Okay, so let's look at another example for angular momentum. A conical pendulum consists of a bob of mass m in motion in a circular path. So we have a circular path in a horizontal plane, as shown in the figure. During the motion, the supporting wire of length L maintains a constant angle theta with the vertical. Show that the magnitude of the angular momentum of the bob about the vertical dash line is given by this expression. Let's take a look at this setup here, the conical pendulum. I have a bob of mass m. So what are the forces acting on this bob? First of all, I see that I have the weight of the bob. So there's going to be an mg here. And because it's connected to a string, there has to be the tension on the string. So this will act on the bob. This is a 90-degree angle. So as a result of these two forces, what is the bob doing? So if I take this vertical line here, it's the same angle theta. So the forces have a component on the radial axis here. So I have to have a force on the radial axis. That's going to be my centripetal force, because as a result of these two forces, there's the radial force. What the bob is doing is it's rotating on a circular path in the xy plane. It's in a horizontal plane. Okay, so this is on my xy plane. So this is, let's say, y-axis, this is the x-axis, and this is the z-axis. All right, and as a result, the motion is on the xy plane. And as far as the radius of this circular path goes, I call this radius r. I can see from the geometry that the radius of the circular path r is going to be equal to L times sine theta, right? Because this part, the distance to the support point, this should be equal to L cosine theta, and this part should be equal to L sine theta. So tangent theta is equal to L sine theta divided by L cosine theta. All right, and I'm talking about the angular momentum. So for that, let me think about where the angular momentum will come from. Because I'm rotating on the xy plane, I have the position vector with respect to the pivot point, that is this r vector here. And then I have, if this guy is rotating on the circular path like this, I will have a tangential linear angular momentum. And what will it be? So it will be tangential to the circular path, and it will be equal to P is equal to mb. So it's the cross product of r with mb that will give me the angular momentum. Okay, now that I understand the setup of this problem, let me concentrate on the forces in order to figure out the relationship between the forces. Now, the net force on the z-axis here, that is the vertical axis, is t cosine theta minus mg. And what is this force equal to? This must be equal to 0, because there is no motion on the z-axis. No motion on the z-axis. All right. So this tells me that the tension on the string is equal to mg divided by cosine theta. On the other hand, I have motion on the xy plane, and it's a circular motion on the xy plane. So I need to have a radial force. Net radial force I have is t sine theta, and this must be equal to, from my knowledge of circular motion, m v squared divided by r, where r is the radius of the circle. So this is going to be equal to m v squared divided by l sine theta, because I have found that r, the radius of the circle, is equal to l sine theta. So if I substitute for tension here, mg over cosine theta, so I have mg over cosine theta sine theta is the radial force, is equal to m v square over l sine theta, and these m's cancel each other, so I find that v squared is equal to l g sine square theta divided by cosine theta. So v is equal to square root lg sine square theta divided by cosine theta. As you can see, this is not only circular motion, it's going to be uniform circular motion, because the angle theta is kept constant in this conical pendulum. So I always have the same angle theta here. So let's note that maintains a constant angle theta. So this is actually uniform circular motion with the speed, constant speed, square root lg sine square theta over cosine theta. Now, the angular momentum of this bob is going to be the r cross product with its linear momentum p. So it's r cross product with mv. And once again, if I look at the figure, the velocity is tangential velocity, so it's perpendicular to the position vector of the bob. So I find that this is mvr, right? Because they're perpendicular. Sine of 90 is 1. And I write for v square root lg sine square theta divided by cosine theta, and then I write for r l sine theta. That was the radius of the uniform circular motion. So this is going to be the magnitude of L that I'm looking for here. So that the magnitude of the angular momentum L is going to be, if I write everything in the square root, I have m going into the square root as m square, g, L goes in as L square, so it's going to be L cube. Sine theta goes as sine square will give me sine to 4 theta divided by cosine theta. So this is going to be my final answer for the magnitude of the angular momentum of this bob. Now, if you're wondering what is the direction of this angular momentum, so let's take a look here. If I use the right hand rule, R cross with P is basically pointing in the negative z direction, right? So if I plot this vector here, this is in the negative z direction, and this is going to be my angular momentum vector. So this is the angular momentum. So if you wish, you can write it. It is in minus k hat direction according to the coordinate axes that I have set up here.